Welcome AP Physics, and good to see you on this Wednesday or Thursday, depending on which day you're zooming in. So today's lesson is going to be the synchronous day, which for Group A is Wednesday and for Group B is Thursday. And on the synchronous day, you will be zooming in at 8 a.m. On the asynchronous day, you won't need to do that. Okay. So yeah, today we're going to be working on vectors as our big idea. So going through our schedule here, you've got your planner link. You can check that out for all the important links that you'll need. And as far as things to turn in today, one thing we are going to do today is we're going to register for Khan Academy. And as you register for Khan Academy, I want you to go ahead and make sure that you get into our classroom. There is the code for the classroom right now. And you want to go ahead and make sure to include your last name with a comma and then your first name as you get into there. The other thing I'd like you to do right now is to register for AP Central, and I've given you the code here. We're not going to do any work with AP Central right off the bat, but we will want to get familiar with that. So you just go into AP Central, and you probably already have registered in the past with an account. If not, you just want to create an account, and then you're going to find our class with the code that you see on the screen right here. Okay. All right, made a mistake there, I had to fix it. Okay, so moving forward here, time goals. Again, our time goals every week are going to be to spend 440 minutes on our class, and I want you to be accounting for your time every day so that we can make sure that that works for us all. So today we're going to focus on the synchronous day learning. So synchronous day learning, you want to go ahead and jump into AP Central and just give a little look around what we're going to do with this course. I've included a link on the website to the AP1 course guide. And if you look in that, it's a huge guide. It's got all kinds of stuff about this class. But to get on top of things and to understand what we're doing, it's a good idea to look through there and see what those resources are. And just realize this is always going to be posted on my website, so you can go back into it over time and take a look at it. We also have a list of all the different topics that we're going to work on this year, and it is going to be a fast-paced year, given that we're only doing this in quarters, and we basically have 2 quarters to cover what we normally would do the whole entire year. We do have more time, obviously, but it just means that we're going to be doing a lot of work in a concentrated period of time. So being ready for that is important. Again, log into AP Central, use that code to get into our classroom, and same thing with Khan Academy. Okay. Next thing, we're going to be introducing the topic of vectors right now. So if you want to go ahead and get out your journal and take some notes in your journal. So the first thing to do is go ahead and watch this intro vectors video from Khan, and that's going to help you get an overview. And just to remember, make sure that your speaker notes are enabled. And so looking down into the speaker notes, you can always see here's the important ideas that go along with these topics. So to start with vectors, I want to start with this idea of what is a force. And in physics, we represent a force as a push or a pull on something, and we represent it with arrows. And so an arrow has both magnitude, okay, how big is it, how strong is that push? It also has direction. So the force is a vector also, because that's also a definition for a vector. Okay. So next thing we want to be starting to get familiar with and comfortable with in physics is being able to draw forces, and we do something called a free body diagram. And when we draw a free body diagram, we usually start off with just like a basic representation of the thing we're drawing, and then we start with a process to put all the correct forces and have them drawn correctly. And so in this diagram right here, in the speaker notes, by the way, I've explained all this stuff really well, but notice if we have a car sitting still, and you want to know, well, what are the forces on that car? You'd start by drawing a car. Okay, it doesn't have to be detailed. It could just be a real stick figure-y kind of thing. Then I would start with like the center of mass of the car. So notice I put an orange dot there. Then I went ahead into drawing one of the forces is pushing down. It's the gravitational force acting on the mass of the car. We call that sometimes the force of gravity. And notice I use the letters mg, because that's actually the mathematical formula for mass times gravity, which is the definition of the force of weight. So I go ahead and I draw an arrow there. And then in my next image right here, I take that arrow and realize if the force of gravity was pushing the car down, but the car wasn't actually accelerating downwards, that's because there's another force that's equal and opposite acting up. In physics, we call that a normal support force, or just the normal force. We give that one the letter N. But one of the things to notice is when this car is in a state of dynamic equilibrium, which it is when it's sitting, let me back up. When it's in a state of static equilibrium, which it is when it's sitting still, the arrows need to be the same size equal and opposite direction. It's kind of like a tug of war, and it makes so the car is actually sitting still. That's the static part, and it's not accelerating. That's the equilibrium part. Okay, so there's a nice drawing for our car sitting still. So noticing a free body diagram for a car that's moving at constant velocity or constant speed. The reason it's moving at constant speed is because all the forces are balanced. Okay, if the forces were not balanced, the car would be accelerating. Now, if you notice in this picture here, you have your weight written as mg and your normal force, just like in the last problem. It's just like it's sitting still. But in this case, the car is actually moving forward. And if you picture yourself on the highway, you're going forward. The car has some momentum, but friction would be slowing the car down if you weren't giving it some gas. Okay, and so notice in this picture, there's the force that the engine is applying to the right, and it's being completely balanced by the force of resistance to the left. And this whole diagram, notice it's all balanced. All the arrows cancel each other out. This is a state of what we call dynamic equilibrium or moving equilibrium. Okay, so that's how you draw something in dynamic equilibrium. And the next one here shows a car accelerating. Now, one of the things to notice in the accelerating process right here is that the engine force is bigger than the resistance force. So there's now an imbalance in those forces. There's a net force that goes to the right. And so what's going to happen with the car when there's a net force to the right is that the car will accelerate to the right. Now, some people confuse that and think, oh, that means the car's moving to the right. That's not what it means. Okay? The car in the previous picture was also moving to the right, but it was in equilibrium. The fact that the arrow is longer means that it's in non-equilibrium. It is not in equilibrium. And whenever you see that imbalance of arrow sizes, that's a sign that the object is accelerating in the direction of the imbalance. Now, can you imagine if the resistance arrow was bigger than the engine arrow? If it was different in this picture, then you would say the car could still be moving to the right, but it would actually be accelerating to the left. And what that means is that it's decelerating. Okay, that's how we normally say that, or slowing down. Okay, but in physics, it's really just an acceleration. We just call it like a negative acceleration. That's all. So understanding the concept of equilibrium. So when you're analyzing equilibrium, realize that no change in motion, another way to say that is no accelerations occur, and the net force, notice the sum of the forces equals 0. There's no net force, and in your drawing, then you're always going to see that the arrows in their respective dimensions, like the x dimension and the y dimension, they cancel each other out and they balance. We call that condition equilibrium. Now, this shows you just like a summary of what we just saw, but this is some different circumstances for static equilibrium, ball sitting on a tee. And notice that the sum of the forces in this case include normal going up and weight going down, but when you add normal plus weight, okay, it's a positive plus a negative, okay, they balance out to 0, and we call that static equilibrium. The net force is 0. When an object is falling at constant speed, like a feather dropping through the air, you do the same analysis, and it's still equaling 0. It's not much different than the previous problem. The difference is it's actually moving, so that's where the word dynamic comes from. It's moving equilibrium. But notice the picture of the car, because the forces are actually not balanced, the force of the engine is bigger than the force of drag, in this case, or the resistance force, then we're in a state called non-equilibrium. And whenever we're in non-equilibrium, there is acceleration happening. Okay. Next picture shows you some basics about net force. Okay, so oftentimes we write net force with the symbol for the sum of the forces. Sometimes we can write it as just net force. But notice in these diagrams right here, they just show you how forces add when they're lined up. Okay, so if things are lined up in a linear fashion, you can just use simple addition and subtraction rules to figure out what the net force is. So look at the car, and notice in that car right there, you've got 10 newtons to the right, 7 newtons to the left. The net force in this case would be 10 minus 7, or 3 newtons to the right. And since it's a vector, you'd actually report that force. You wouldn't just say 3 newtons, you'd say it's 3 newtons to the right. The direction is part of that also. So understanding what vectors are in general. Vectors are quantities that have magnitude and direction. And in physics, we define vectors by drawing arrows. And the length of the arrow, we scale that up to the magnitude. And oftentimes we'll write the number of the magnitude. So for instance, in this case right here, the magnitude of that red arrow is 32 meters per second. And we also need to report the direction of the arrow. And that gets confusing for people sometimes because you have to ask yourself, when I pull this angle right here, how do I measure that angle? Like if I took a protractor on there and I just put the protractor, my protractor would read 52 degrees. And you can put that down there, but that doesn't tell you necessarily which direction it's pointed. So usually for our conventions, you're going to start with your baseline, okay? And if I look at this picture, I see north is my baseline. I'm going to pull my direction from north. And so then I'm going to report the direction that the arrow moved from north is toward the east. And so I'd actually report that as east of north, okay? I could have done it a different way. It would still represent the same direction. I could have pulled it from east and pulled it north of east, and then I would report that as, what would that be, 90 minus 52? Okay, so that would be 38 degrees. What would that be, north of east? Okay, so you see how that works. All right, scalar quantities have magnitude only. Okay, so they're different from vectors. We just report a number, and we don't need to report a direction. When we add vectors, we just talked about when we add them linear. Okay, but when we add them when they're at angles to one another, we do a process that we call vector addition. And when we're not using math, when we're just doing it by like lining up the vectors, we call this graphical method. And this is just sort of like a way that we can draw vectors out to scale and then put them together. So let's just say I have a vector A, and let's imagine this is like a force. Okay, and we can imagine it's like you kick a soccer ball. Okay, and when your foot kicks the soccer ball, it's putting a force that goes in that direction on the soccer ball, we'll say. Then another direction of B right here, another vector, is like another person kicking the soccer ball. But let's say two people kicked it at the same time, and they both kicked it in different directions. What would the ball do? Okay, the ball wouldn't react to just A. It wouldn't react to just B, but A and B would kind of blend together and it would go in a direction that's somewhat between those two. And that's what we use vector addition for. And we go ahead and do it like this. Okay, so notice we do this thing called head to tail vector addition. So I just went ahead and took this vector and I redrew it here. I took this vector here and I put the tail of it on the head of this one. Head to tail. Okay, and then notice the direction, and then I just draw between those two, and that turns into the resultant vector. And so like the case with the ball being kicked from two directions, this would be the result of it. It would go off in this direction instead. And that's what we call a graphical method of vector addition. So here's a couple examples of how to do graphical method of vector addition. And again, don't forget about the speaker notes. All this information that I'm talking about is in here. But let's imagine we have two pirates. We've got this really muscular arr and this big-bellied burl, and they're both trying to move this pirate chest of gold to their pirate lair. Now, they both have different interests. R is really strong, and he has this vector A going on. So the fact that this A is bigger than the B is because he's pushing really hard compared to big-bellied burl. And if you look at the vector direction compared to burl's, they're both pushing it. But imagine that this chest is going to go somewhere between these two. Okay, and we can use two methods. One's called parallelogram method. The other one's called head-to-tail method to determine what would be the actual motion of the treasure chest as a result of both of those guys pushing it on the same time. Now, if we use the graphical method called parallelogram method, it looks kind of like this. We put the two vectors tail to tail. Notice the heads are over here. And when I do that, I draw a parallelogram. I make this line the same length as this one, okay, and just draw it at the same angle. Same length, same angle, and then I just connect the corners, and that represents the resultant vector that's going to result in moving that treasure chest in the direction and with the strength of that red arrow right there. Okay. Now, a simpler way to do this is something we call the head-to-tail method, and this would involve just taking this vector and this moving B up to here, okay, or moving A down to here. I could do either way, but we want to set the two vectors head to tail, and notice this is head to tail, and then you can see the resultant vector. And if you notice the two vectors, this one and this one, same result. Okay, so either way gives you the right answer, head to tail method or parallelogram method. Okay. All right, now we're going to deal with vectors mathematically through right angle trig. So if you're a little rusty on right angle trig, your SOHCAHTOA rules, there's a trig review that I put in here. This is only if you need it. But if you're rusty on that, go ahead and watch this Khan Academy trig review just to remember your SOHCAHTOA rules. And here's a couple problems you can practice on the vector practice problems at the end of this lesson. So SOHCAHTOA, you got Charlie pulling a rope at an angle of 42 degrees. And so imagine here that he's pulling up at that angle, okay, with a force of 25 pounds. So he's pulling that rope. What are the x and y components of Charlie's pull force? Okay, so components are the parts of the resultant vector. Like his pull is the resultant vector, but it has an x and y part to it, or an x and y component. Okay, and so I've gone ahead and solved it for you here, but I use SOHCAHTOA. And so I draw it. I say, like, here's the vector that Charlie pulled with. Here's the x and y components. Actually, I'm sorry, I'm on the wrong slide. Back up. Here's the vector that Charlie pulled with. Here's the two components. But notice if I have hypotenuse and I have angle, and I want to know two sides right here, I can tell you that if I want to know the y part first, that's an opposite side. And a sine function, the SO of SOHCAHTOA, says that the sine of the angle equals opposite over hypotenuse. So, right, I have hypotenuse, I want opposite. Opposite, I'm just algebraically manipulating this. Opposite equals hypotenuse times the sine of theta. The opposite is the y that I'm looking for. The hypotenuse is 25, and the angle is sine of 42. Put that in my calculator, just say 25 sine of 42 equals 16.7 pounds. That's what the up is. I do the same thing with a cosine function, and I figure out what the adjacent side is. Remember, it's SOHCAH is cosine equals adjacent divided by hypotenuse, and then I can go ahead and get 18.6, and those are my components. Okay, that's a skill you'll need to use a lot in physics, so get on top of your SOHCAHTOA rules. Next one here is sort of doing it in reverse. Okay, let's say we have a model airplane that provides a 45 Newton thrust directly north. Okay, north is up. Wind is providing a 30 Newton force directly west. And so notice with north and west, the angle that goes between those is a 90-degree angle. So I'm using 90-degree angle trig. What is the net force? That's going to be the hypotenuse between those x and y components. And what would be the magnitude and the direction? Okay, so in order to solve those kind of problems, I need to go ahead and draw out my triangle with the two sides. And I'm just trying to solve angle and hypotenuse. Okay, so I would go ahead and use the sum of the forces, is magnitude and direction. Pythagorean theorem, a squared plus b squared equals c squared, is going to give me the hypotenuse as a magnitude or a number. And if I want to get to my angle, I'm going to use an inverse function in trig. And because I have two sides here, I'm going to use an inverse tangent function because I've got my opposite and adjacent sides. And I show you the work here. So notice I just drew out, here's my two forces, north, west, head to tail vector addition, hypotenuse, using the hypotenuse Pythagorean theorem, inverse tangent, notice the math around inverse tangent gets me an angle, and then I report it as 54 degrees at 37 degrees, but now I have to be careful about how do I report this whole west of north thing. That's one of the most confusing things for people. But notice I drew my angle here. This is my baseline that's already lined up in my north, east, southwest quadrants. And so if I take my north line and I pull my angle toward the west, then I'm going to report this as it's west of the north line. Okay, so that's kind of how we report an angle like that to make sense of that angle. All right, next thing, a couple practice problems. So we're going to go ahead and practice some basic vector addition here. And so notice like these two opposite directions cancel. Okay, these two right here go into trig. I could draw this if I wanted to make a triangle, slide that 4 over and make a 3, 4, 5 triangle. Notice this one here, I've got the 2 and the 5, they net out to 3 down. Notice this one here is 10 and a 3, they net out to 7 to the right. Okay, and then just using some trig, and then I just show you how to do that here. So just getting on top of that. Okay, and a little summary. What are vectors? Vectors are representatives of quantities that have both magnitude and direction. We use arrows. The length of the arrow represents the magnitude. The angle is going to be pulled off of some northeast southwest line. The the components. We have an x component and a y component. You can use trig to figure out your x and y components. And we also have the resultant, which is the hypotenuse, which is oftentimes the net force that we're looking for. We can use Pythagorean theorem to figure things out too. So next one. So that was basically our vector lesson. Okay, and then I've got the vector practice problems here to practice with right after you're done. This one here is going to be done on your own. You can use partners to help you, but everybody needs to turn in their own. And you're going to go ahead and do all your work in your journal with this, label the title carefully, label all the numbers carefully, and then you're going to turn this in by way of Google Classroom. Okay, so that's it. And so there is a text reading that goes with this that I'm not assigning today, but if you want to jump ahead, it's in the next lesson right here. And it would also help you and support these things. So you could maybe just like open up the text reading and just like check it out if you wanted to, and then use that without actually doing the reading, but see if it helps you with the practice problems when you get to those. Okay, don't forget to do the daily reflection form by 3 o'clock today. Everything else is good. You guys have a great day. It's a great day to be at Lakewood Tiger. Arr!